Let us recall the last session on the first law of thermodynamics applied to an open system. We have taken this system for our consideration. So this was recalled some 2 minutes. So it's an open system because there is a mass transfer as well as transfer there. Let us assume it is steady flow energy equation. That is, the flow doesn't vary with respect to time and space. So it is S of E. The properties of inlet are P1, so is equal to V1, mass is C1, temperature in Kelvin is T1. Similarly, the properties of the liquid are P2, so is equal to V2, temperature T2, and the mass is C2. And let us assume a data bed. From the side, we will measure the height. So let us define this height as Z1 and corresponding at the exit. Let us assume this height to be Z2. We know the first law of thermodynamics operated in open system is given by Q equal to W plus delta E. Yeah, W plus delta E. This delta E may be in the form of
kinetic energy,
kinetic
energy, and internal energy.
Then kinetic energy,
Potential energy and internal energy.
and it is very good. And the internal energy. It is I. This work has two components, that is displacement work and flow work. The flow work is done by P2 V2 minus P1 V1. Flow work is done by P2 V2 minus P1 V1. And the kinetic energy is given by half m C2 squared minus C1 squared. And the potential energy is given by mg into Z2 minus Z1. And the internal energy is given by m into U2 minus U1. And when I put here as V2 a specific volume, which means the mass is 1 kilogram, which means it's not to put the mass because it's understood it is 1. So it is also 1. So what we consider is that the flow through this medium is, or the mass flow rate is 1 kg per second. So m dot equal to 1 kg per second. So that I made this one m equal to 1, and here also m is 1, and here also m is 1. Now this u is small u, which means its specific essence is nothing but intensity property. As I told you earlier, you replace all the terms with negative to one direction, so it will become u1 plus p1 v1. First I have taken this term, then this term, plus half c1 squared, this term, plus g z1, this one, plus q equal to u2, this term, plus p2 v2, this one, plus half c2 squared, plus g z2, plus w. So this expression is nothing but steady flow energy equation, what I did in the last session also. As well as we know what is v1 plus p1 v1, it is h1. So it is h1 plus half c1 squared plus g z1 plus q equal to h2 plus half c2 squared plus g z2 plus w. So this expression is called as steady flow energy equation when the flow of fluid is considered as 1 kilogram per second and the mass flow rate is 1 kg per second. Let us derive or let us deduce this steady flow energy equation for various applications like what we saw in the earlier class, like nozzle, diffuser, turbine, compressor, fan, pump, and heat exchanger, as well as the throttle valve. As well as we should know the general formula for enthalpy is given by mCp delta T, and the general formula for enthalpy is given by mCv delta T. And if I am going to have small h, is nothing but Cp delta T. What is then small h? Small h is nothing but capital H by m. If you are going to bring this h by m, it becomes a small h. Otherwise, the unit of h is kilojoules, the unit of small h is kilojoule per kilogram. It is specific essence, otherwise called internal or intensity property. Similarly, small u will be equal to CV into delta T, which is nothing but capital U by M. This also has a unit of kilojoule per kilogram. It has a unit of kilojoule. So we should know to differentiate the efficiency property and specific efficiency, which is nothing but intensity. So now these two things we should know. Now let us take the case of nozzle. Let me take the case of nozzle and diffuser. So in the morning itself we told the nozzle is used to increase the velocity at the exit, or is used to increase the kinetic energy of the flow at the exit. And the diffuser is the reverse of nozzle, that is, the diffuser is used to increase the pressure at the exit. Okay, so let me take the case of nozzle. This is the nozzle. The nozzle doesn't have any moving parts. So we can see there doesn't have any moving parts, which means the order will be 0. Order will be 0, but there will be flower. So let us say this is section 1-1. This is section 2-2. So let us try to adopt the same energy equation here, absolute energy equation, which is nothing but H1 plus half C1 square plus GZ1 plus Q is equal to H2 plus half C2 square plus GZ2 plus W. Now, what about work in a nozzle? Work done in a nozzle. What is the value of work done in a nozzle? 0. Because nozzle is a device which is not meant for producing any power, or doesn't consume any power also. Like compressor doesn't need any power. It's just like a geometrical arrangement where it has only variation in the geometry. Because of the variation in the geometry, we are able to obtain the increase in the velocity. So we know that W is 0 because there is no heat work added, or there is no work is being supplied by the system. It is not a power consuming or power absorbing device. What about the heat transfer? Can you 0? Why is 0? Whether the fluid doesn't have any heat, the fluid has heat, but the heat is not transferred from the system to the surrounding or from the surrounding to the system, which means the nozzle is perfectly insulated. So it's made adiabatic. So we assume there is no heat transfer from the system to the surrounding or from the surrounding to the system. But definitely there will be change in H1 and H2. The heat will be converted into some other form of energy. That is actually applicable. But we assume that there is no heat loss. Here the Q indicates heat loss to the surroundings, or there is no heat gain from the surroundings because of the temperature condition. And mostly the nozzle will be placed horizontally, and hence the value of Z1 will be equal to Z2, and hence we can assume Z1 equal to Z2, which means Z1 will be equal to Z2. So both will get cancelled away. Both will be getting cancelled away. So what is the final formula we will get? H1 plus half C1 squared equal to H2 plus half C2 squared. It is for nozzle. This substitution order derivative is for nozzle. Let us take the case of diffuser. So this is nothing but diffuser. This is nothing but nozzle. In a diffuser, what about the work done? 0 because there is no moving parts. W equals 0. What about the heat loss? 0. What about Z1 and Z2? Let us assume both the same. So Z1 equals Z2. So what about the expression? The same expression. So the expression for the nozzle and the diffuser remain the same up to here. So there is no difference between the nozzle and diffuser up to this particular region. So this formula is applicable to both nozzle and diffuser. In case of nozzle, C2 will be comparatively higher than C1. C2 will be, if you are going to take the case of nozzle, my value of C2 will be greater than C1. In case of diffuser, what will happen means H2 will become greater than H1. What is H2? H2 is nothing but U2 plus P2 V2. We should be greater than U1 P1, U1 plus P1 V1. Which means What is the final attitude?
P2 should be more than.
Yeah, my objective is that either H1 is greater than H2 is greater than H1, but my primary objective is that P2 should be more than P1. That is the diffuser's device which is used to increase the static pressure. So don't feel there is no pressure term. The pressure term is hidden inside the enthalpy term. So our objective of the diffuser is that the P2 should be greater than P1. Okay, very good. Now let us move to the nozzle. So you know how to derive the steady flow equation for the nozzle and diffuser and how the terms have been interpreted. Now let us move to the nozzle, and compared to C2, generally the value of C1 is negligible. Compared to the value of C2, the value of C1 is generally negligible. So this value, this equation becomes H1 equal to H2 plus half C2 square. From this, what is our objective? To find C2, to find the exit velocity. So it will be H1 minus H2 equal to half C2 square. Otherwise, C2 squared equal to 2 into H1 minus H2. Otherwise, C2 will be square root of 2 into H1 minus H2. So what is C2 from here? C2 will be equal to, what is H1 minus H2? Cp into T1 minus T2, because we know that small h is given by Cp delta T. It is not can even put delta H. So here the delta H will be given as 2 Cp into T1 minus T2. So if we know the inlet temperature and the exit temperature, it is possible to find the velocity of the nozzle. If the even other parameters are not given, in your examination, they may give, there is a heat loss of 0.5 kilojoules per second. Then I can't make Q equal to 0. There you have to put the value of Q. In some problems, they will tell the nozzle is not horizontal, the nozzle is inclined such that Z2 is 3 meter above Z1. Then I have to put Z2 minus Z1 equal to what? 3. I can't neglect. So what we derive is for the general case. But in a particular problem, in the examination, if they are going to ask to consider the heat transfer as the data height, then you have to consider. This is for the general case. Now I hope you can understand the steady flow equation and you know the expression for getting the exit velocity in case of a nozzle. Shall I move to the next topic? Okay. Now let us move to turbine. So we can see is nothing but a turbine. So we can see the diagram of diffuser and turbine looks the same, isn't it? For diffuser also I have drawn a similar diagram. But what are the difference? For diffuser also I have drawn like the same thing.
Here the working substance is different.
Here both can be both can be steam. In case of turbine we are going to give the steam at a very high pressure. It's a isopropyl steam at higher temperature. It's not with respect to the working speed. Then what is the difference? I have drawn for diffuser also the same diagram.
It's a power producing device.
Yeah, that's based on the application. Based on the arrangement I am doing. You are told this is a power producing device, very good. It will develop mechanical power.
It will increase the pressure, sir.
It will not increase the pressure. Here the pressure will drop. Diffuser only it will increase the pressure. But here the pressure should drop, the fluid should expand, then only it can produce power. So what are the other difference between the turbine and diffuser?
Yes, some blade.
Yeah. Even though we are drawing the same diagram for both diffuser and turbine, in case of turbine we have rotating components, moving blades. In diffuser there is no certain things. It's only because of geometry. Here not only the geometry, but the impact of blade is also important. The impact of blade is also impacted. So even though I am drawing a turbine like this, in your mind you have to imagine there is a rotating components inside this one. And definitely the turbine should produce power. So what is the steady flow equation? H1 plus, so if you want you can take, this is the inlet is section 1 and the exit is 2. Okay, every time it is understood. So outside to this is nothing but my surrounding and this is nothing but my boundary. Okay, H1 plus half C1 squared plus G Z1 plus Q is equal to H2 plus half C2 squared plus G Z2 plus W. Plus W. What about W in case of turbine? Whether W will be there or not? It It will be there along with the flow, along with the P2, V2 minus P1, V1. There will also be power produced by the turbine because these are rotating components. When the steam is going to come in heat, or even the water is going to come in heat, the blades may rotate. The blades may rotate. Whether W is positive or negative?
Positive.
Positive, because work is produced by the system, it is positive. What about Z1 and Z2? Let us assume both are at the same height. Because we have drawn like this only, isn't it? Now this Z1 will be equal to what? Z2. So they cancel away. What about the heat transfer in a turbine? It will be
Negative.
negative means what?
Heat lost by the system.
Yeah, whether the heat loss will be in the turbine. It may be there, but generally when you are going to derive it, the turbine is not aimed to have any heat loss. The turbine is not intended to have any heat loss. We assume it's perfectly insulated. There is no there is no heat loss from the turbine to the surrounding or from the surrounding to the system, because we want to convert the heat energy into only work. If you are going to lose this, then your active production of work will get spoiled or will get reduced. So in order to overcome that, we assume generally to make it perfectly insulated. So the intention of the turbine is to produce only power. The intention of the turbine is to only to produce the power. So what about our expression now? H1 plus half C1 square is equal to H2 plus half C2 square plus W. Is capital plus work done. But in the problem they may give, there is some heat loss. Then you have to include Q. Then the Q will be positive or negative?
Negative.
Negative, because heat loss is exothermic, so it's negative. So that will come to a particular problem. But general expression for the turbine is this one. H1 plus half C1 square equal to H2 plus half C2 square plus W. What is the expression for a compressor? What is a compressor? The compressor looks like. The compressor looks like in the opposite direction. Okay, how will a compressor looks? So the compressor will looks like,
Nozzle.
yeah, very good. The compressor looks like a nozzle. But what is the difference between the nozzle and the compressor?
So it has also rotating components.
It also have rotating components, so it can absorb the power. So what will be W in case of compressor?
Negative.
Negative, but W will be there. What about Q? We assume Q is 0. We assume Q equal to 0. So what is the expression? The same expression. So the expression for the compressor is also what? The same expression. But when you are going to substitute the values, you will find that W will be negative, which means compressor is a power absorbing device or work absorbing device. In the same formula, if you are going to use for turbine, W should be positive. If it is going to be negative, you have made mistake in the problem. In the case of compressor, W should be negative. Otherwise, you have made some mistakes. Similarly, this formula holds good not only for compressor, but also for blower, but also for fan. So, what are the difference between blower, compressor, and fan? All are work absorbing devices. W will be negative. But what is the difference between compressor, blower, and fan? It is the pressure ratio. It is only the pressure ratio. In case of compressor, the pressure ratio will be very high, say more than 6 or 10. In case of blower, it will be 1.15, 1.5 like that. Fan hardly greater than the atmospheric pressure. So all are nothing but what? Power absorbing device. So H1 plus half C1 square equal to H2 plus half C2 square plus W. So the expression remains same for turbine, compressor, blower, and fan. In case of turbine, when I substitute in this equation, I should end up with the W with positive. When I go to substitute for compressor, blower, and fan, W should be what? Negative. That's it. So we'll move further. Okay. Can I go for pump? Instead of compressor, fan, and blower, let us go for a pump. I will sketch it normally. So it is pump. It is 1 1. It is 2 2. So if you want to mark, you can mark it as 2 2. It is 1 1. So what is the expression for pump? The pump also have what? Rotating device. Whether W will be there? Yes. Whether Q will be there? No, Q will not be there because pump is going to handle only water and hence mostly there will not be any heat loss. But if you are going to pump a heated oil, then Q may come into picture. But generally we assume the entire arrangement is insulated. So Q is also 0. So the formula becomes what? H1 plus half C1 square equal to H2 plus half C2 square. In case of pump, when you are going to handle a incompressible fluid, almost C1 will be equal to C2. Almost C1 will be equal to C2. Whereas in case of blower or fan, C2 may be different, C1 may be different. But in case of pump, the velocity remains almost same. Which means this expression further reduces to H1 is equal to H2 plus W. Why? Because in case of a pump, C1 will be almost equal to C2 because it handles an incompressible fluid like water or oil, etc. Now what is W? W will be equal to what? H1 minus H2 from this expression. What is H1? What is H1?
U plus P.
Very good. So it is U1 plus P1 small v1 because we are considering for unit mass. Whatever we are deriving is that we are considering the mass of the fluid is 1 kg per second. If you want for 5 kg per second, you multiply by 5, you get the corresponding answer. Minus, what is it? H2? U2 plus P2 V2. From this, what is the expression you get? U1 plus P1 V1 minus U2 minus P2 V2. Isn't it? What about U1 and U2? They will remain same. Why? There will not be any change in internal energy. Because U is a function of temperature. There will not be any change in temperature, which means there is nothing to worry about U1 and U2. The value will remain same. So we can cancel off U1 and U2. So finally, what will happen to W for the pump? It will become P1 V1 minus P2 V2. What is V1?
Specific volume.
At inlet. What is V2?
Specific volume.
Outlet. So whether the volume of the water will changes same. The volume of water cannot change. The same amount of volume will be sucked at inlet. The same amount of volume will be sucked at outlet. So one more assumption is that V1 will be equal to what? V2. Okay. Yeah, fine. If I am going to have a 1 liter of water bottle, if I am going to even compress it, I can't reduce its volume. The volume remains same. Even if I am going to lift water from the ground level to the top level to 10th floor, the volume will not change. So the specific volume will not change. So V1 will be equal to V2, which means W will be equal to V of P1 minus P2. V of P1 minus P2. What about pressure P2 will be greater than P1 or less than P1? What is pressure P1? You have to suck the water from the underground. That is P1. What is P2? Delivery head. Whether this P2 will be greater than P1 or not?
P2 is greater.
P2 will be greater than P1. Otherwise, if you are going to confuse the suction head and the delivery head, you may have a doubt. Let us not worry about the suction head and delivery head. Now I have a rotating component. The pump will have a rotating component like a blades will be there. Okay, the blades will be like this. So it will suck the water. It will suck the water because of this thrust force. It will push the water up. So whether this compared to this pressure is called as P1, this pressure is called as what? P2. Let us not worry about suction head and delivery head. It may confuse you. So I am telling the water is coming here, and because of the suction and because of this rotation of this blade, the water is thrown away and is going to be lifted. So compared to P1, what about the ratio between P1 and P2? It should be higher. P2 because of suction. Here the negative pressure. Here is delivery. So P2 should be greater than P1. So which means now our value of P2 will be greater than what? P1. So what about W? It will be positive or negative?
Negative.
Negative. Because P2 is greater than P1, V1 can also be greater than negative, which means this expression will end with a negative answer. Whether negative is right or wrong?
Work observing machines.
Yeah, here the negative doesn't show say wrong because the negative sign indicates that work is being observed by the device. The pump definitely will observe the thing. So the expression is right. So the expression is right because P2 is greater than P1. This expression will end with the negative sign. The negative sign indicates it's a work power consuming device or work absorbing device. So it's right. Okay. Now whatever we derived is for what? For 1 kg of the fluid. For 1 kg of the fluid. Now let us multiply by the mass. For any mass of the fluid. For any kilogram of the fluid. So m into what? Into specific volume into P1 minus P2. What is unit of mass? Kilogram per meter cube. What is the unit of specific volume? What is the unit of specific volume?
Meter cube per kg.
Meter cube per kilogram. Very good. Into P1 minus P2. So this meter cube, yeah, this it's not a
Mass kg.
yeah kg per second. Let me assume it is a kg per second. Okay, it's not only mass, it's mass per weight. Let us assume it is a mass per weight. So it is a kg. I can't strike out meter cube. It will be meter cube. I can strike out what? Kg and kg. So the answer will be what? Meter cube per second. What is the unit of meter cube per second?
Discharge.
It's discharge or volumetric flow rate. Very good. It's nothing but a discharge or volumetric flow rate. Generally, we used to keep this term as Q dot in fluid mechanics. But already we have Q for heat transfer. So, not to overcome the same letter, let us use the term capital V dot. Capital V dot once again indicates what? Volumetric flow rate, because the unit is what? Meter cube per second. So, it is V dot into P1 minus P2, which will take care of the mass also. Which will take care of any mass. If you want to go with 1 kilogram of mass, then you go with this formula alone. If you want where V is nothing but specific volume of water. If you want to go with any mass, any kilogram of mass, then it's better to go with volumetric flow rate. In any fluid mechanics book, they used to give us W equal to Q dot into delta P. Here Q dot is nothing but the volumetric flow rate. Here instead of Q dot, we are mentioning the same term with V dot. That's it. But the meaning remains the same. So this is nothing but a pump. In the pump, there will not be much heat transfer, and there will be only work transfer will be there, because we assume that temperature remains the constant. So we have derived the expression for the pump also. So the last thing we will derive, and we'll see one more problem. What is throttle? What is throttle valve? Today morning we discussed. So throttling.
It's a temperature reducing device.
Yeah, that is one of the, because of the Joule suspension. It may also happen when there is no temperature drop also. There is another application. Yeah. So here the steady flow equation is H1 plus half C1 square plus G01 plus Q is equal to H2 plus half C2 square plus GZ2 plus W. Whether any rotating part is there in the thing, in this throttle valve or expansion valve? No. So W will be equal to what? 0. If there is any heat transfer? No. Heat transfer, whatever I meant heat transfer, is not from the system to the surrounding.
Inside.
Yeah, it is the system now. It is nothing but your porous media. Whether I am asking you any heat loss is there from the system to the surrounding,
No.
or from the surrounding system is not there. So Q is 0. What is the heat transfer you are telling means it is happening through this opening. That is different. That is happening within the system. It is not happening away from the system. It is happening within the system is not considered. We are talking only about the heat loss or heat gain from the surrounding. Okay. Okay, fine. So Q is also not there. And let us assume there is a delta meta state. And when you are going to allow this air or gas to pass through the porous media, what will be the velocity of this air? It is going through the porous media. Let us have this is the porous media. Isn't it? The porous media have many fine holes.
Velocity will increase.
Velocity
Very less.
very less. The velocity will be what? Very less. So C1 will be almost equal to C2. Because a lot of obstacle is there. It will be absorbed. It will be coming slowly. It will try to diffuse it. It's like a diffusion mechanism. Not actually diffusion, but it's just like a diffusion mechanism and try to escape. And hence the velocity variation will be much more. Which means C1 square will be equal to what? C2 square. I can assume C1 is equal to C2. Even if I have a small opening, also the opening should be very small, such that the C1 will be equal to what? C2. There will not be much variation in the velocity. Which means finally we end up with H1 equal to what? H2. So in a throttling process, the final formula what we derive is that the enthalpy remains constant. The enthalpy at the upstream and the enthalpy at the downstream will remain constant. So I hope we have covered almost all. And one more thing is left. It is nothing but our heat exchanger. It is nothing but a, we have not covered this topic. So where are the places you find the heat exchanger in a power plant? It can be an evaporator, it can be a condenser, it can be a cooling tower, it can be a normal shell and tube heat exchanger where you want to exchange the heat between a hot fluid and a cold fluid. Okay, so there are many applications. It's also an open system. Why? Mass transfer as well as heat transfer. Let us assume a single cylinder tube flask. heat exchanger. Okay. Okay. Now, from this end, yeah, let us say hot fluid is coming, H1, or yeah, hot fluid 1 is coming. Here, I am going to send the cold fluid, cold in. I am going to send the cold in. Now the hot fluid is going from left to right. It is going to pass. Let us say this is section 2. It is hot fluid at exit. I will put a hot out. Here I will put a hot in. Okay. Here I will put cold in, and here what become cold out. Now what will happen? Means this fluid is at a higher temperature compared to this fluid. This one is called hot fluid. This is called cold fluid. Let us assume this fluid is coming at 500 degrees Celsius. Let us assume, and this fluid is entering at 300 degrees Celsius. This fluid will circulate over the shell. This fluid is called shell fluid. This fluid is called tube fluid. Now there is a heat exchange take place between these two fluids. Not direct mixing, but indirectly the heat will be transferred from this fluid to this fluid. So what will happen to the temperature of this cold fluid when it is going out?
It will increase.
It will be more than 300. Definitely will be more than 300. Let us say some 350 or something. I am telling you approximately. Similarly, the temperature of this fluid should decreases. Okay, so let us say less than 500, 450 or 475 or even 400, whatever it may be. But definitely less than this one. Now I want to apply which equation? I want to apply this steady flow equation for this particular application. But instead of one fluid, we have two fluids. We have two fluids. Now the same expression H1 plus half C1 square plus G Z1 plus Q is equal to H2 plus half C2 square plus G Z2 plus W. If we have any more rotating components, no. Then W will be there? No. Because either W will not be absorbed, either W will not be positive or negative. And we assume Z1 equal to Z2. Z1 equal to Z2. Now, what about the heat transfer? Yeah, the heat transfer will be there. H2 minus H1. Heat transfer will be there. Here the heat transfer, what I am telling is not from the system to the surrounding or from the surrounding to the system. That is not the heat transfer I am talking. Once again, I am not talking about the heat loss. So far we are using this Q for the heat loss from the system to the surrounding or from the surrounding to the system. But here I am not talking the heat transfer which is happening from the system to the surrounding. I am talking about the heat transfer which is happening between these two fluids. Which is happening between these two fluids. That is the use of the heat exchanger. What is the heat exchanger? It should exchange heat between two fluids. The heat lost by one fluid should be absorbed by the other fluid. That is the concept. So here heat transfer does not indicate a loss, but in terms it indicates how much amount of heat is being transferred from the hot fluid to the cold fluid. Here also we assume there is no heat loss from the system to the surrounding, either from the hot fluid or from the cold fluid. Here also we assume that heat loss is zero. But here the Q represents the heat exchange between the two fluids. So you should be very careful and you should not confuse yourself. So Q is equal to H2 minus H1 plus half into C2 squared minus C1 squared. Got the logic? So once again, the purpose of a heat exchanger is to have the heat transfer. Yes, we have Q. If this Q is going to be positive, it's going to be endothermic. If this Q is going to be negative, it's going to be exothermic. But all this heat transfer is taking place within the two fluids. Okay. I will take another example so that it will be very clear for you to understand this heat exchanger. This is one of the example. Are you okay with this example? Here the heat transfer is taking place within the two fluids. Now let us go for another example and find the expression for this steady flow equation. I am having a system. I am going to pass air, some atmospheric air. Say let us say 30 degrees Celsius. I am going to pass through the system. It is our system. Before it enters is 1 and after the system is called 2. Now you are going to give heat to this heater by means of electrical power supply. So what is the outlet temperature of this air? The inlet temperature is 30 degrees. You are going to heat this room by a heater. So what is the outlet temperature?
will be higher than
Higher than what? 30 degree. Say it is 50 degree. Let us assume. Or else let us take a case of cold countries where the temperature will be hardly minus 5 degrees Celsius. Because of using heater, the temperature rises to say now to 50 degrees Celsius. Got it? So this may be more appropriate. So the temperature, incoming air temperature is minus 50 degree, but it will be comfort to the human. So I am using heater. When the room is get heated, so the outer temperature of the air is 50 degrees Celsius. Whether here heat transfer take place or not. Yeah, because of heat transfer only, the air is get heated from minus 50 degrees Celsius to 50 degrees Celsius. Here also I assume there is no heat loss from the system to the surrounding or from the surrounding to the system. Got the logic? Here the atmosphere temperature will be what? Minus 5 degrees Celsius. But when it get heated, what will happen? The heat tries to move from here to here because of the higher temperature. But assume the entire room is insulated. So this heat loss we are not considering, but we are talking about the heat transfer which is taking place for the air by heating it, by using a filament, by using a heater, So let us come now. H1 plus half C1 squared plus GZ1 plus Q is equal to H2 plus half C2 squared plus GZ2 plus W. What about W in this case? In this case of heater, it is 0 because there is no moving components. What about Z1 and Z2? Let us forget. Let us assume it is in the same data height. What about Q then? Q will be equal to what? H2 minus H1. Why H2 minus H1? H2 will be more compared to H1 because I are adding heat. Plus half into C2 squared minus C1 squared. Definitely this value will be positive. Why this value will be positive? Because H2 will be more than H1. When Q is positive, what does it mean? Endothermic. Heat is added to the system. The other can also happen in case of air conditioning. In case of a heater. In case of air conditioning, what will happen? The inlet temperature will be 30 degree. Whereas by using a air cooler, air conditioning system, the outer temperature will be once again what? 20 degrees Celsius. Now the same expression will come. But what about H2? H2 will be less than H1. So it will become what? Negative, which means exothermic. It has been removed from the system. So the same expression holds good. So you should be very careful what is the meaning of actual Q. The actual Q doesn't indicate here the heat loss from the system to surrounding or from the surrounding to the system. Here the Q indicates the real heat transfer that happens within the system. Within the system is nothing but the within the for this case is air. I hope it is clear. Let us probably solve a numerical problem so that you can be very confident how this system works with all the different types of open systems. Let me take down a problem. So here we have a 3 device. The first device is nothing but a heat exchanger. So what is the purpose of heat exchanger?
to exchange heat
To exchange heat between two fluids or between a fluid itself. To exchange heat, that is the main thing. Okay. Then after this it enters a turbine. So the turbine will be expanding. After the turbine is going to enter a nozzle. It's going to enter a nozzle. This nozzle is called as convergent divergent nozzle. It is not called as normal convergent nozzle. It is called as a CD nozzle. Convergent divergent nozzle. It is nothing but a turbine. It is nothing but a heat exchanger. So now the open flow system consists of 3 components. It's a heat exchanger is the one. So the inlet to the heat exchanger let us indicate by 1 and the exit of heat exchanger or the inlet of turbine is designated as 2. The exit of the turbine or the inlet of the nozzle is designated as 3 and after the 3 or the exit of the CD nozzle is called as 4. So they are given some data. Let us take this data. The temperature of air is coming. The temperature of air is 50 degrees. So T1 is, please try to convert this Celsius into Kelvin by adding 273. So it becomes 280 Kelvin. Don't try to solve the problem by Celsius. Your answers will be wrong. So the first step is to convert the D Celsius into Kelvin. Whenever you see capital D, is Kelvin. So it is 288 Kelvin. So air is coming at a temperature of 15 degrees Celsius. Is passed through a heat exchanger at a velocity of 30 meters per second. So C1 is what? The air is coming at the velocity of 30 meters per second. Whereas temperature is raised to 800 degrees Celsius. So before the heat exchanger, temperature is only 288. After this heat exchanger, the temperature is raised to 800 degrees Celsius. Please once again don't forget to add 233 to convert it into Kelvin. So from 288 Kelvin, the temperature is risen to 2073 Kelvin. So what has happened here? The temperature has risen from 288 Kelvin to 1073. What has happened here?
Heat transfer.
Heat is transferred. That's what we want in a heat exchanger. Heat is transferred. So what is the question they may ask? How much amount of heat is added to the air to rise from 288 Kelvin to 1073 Kelvin? This is the question they may ask. This is the only possibility. Got the logic? So it should be in a question to frame the question. It then, after here, it then enters a turbine with the same velocity. So they assume the velocity is same. So they assume the velocity, there is no rise in the velocity. With the same velocity. And it expands. Because the turbine it has rotating component, it expands until the temperature falls to 650 degrees Celsius. So the temperature is what? 650 degree. So what are the immediate step? We have to add 273 and convert it into Kelvin. So it is 903 Kelvin. So from 1073 Kelvin, the temperature drops to 903 Kelvin. What is the purpose of a turbine? It produces some useful mechanical work. So the question is what? How much amount of work will be or power will be generated by the turbine? That may be the question. Okay. On leaving the turbine, the air is taken at a velocity of 60 meters per second. So on leaving the turbine, the velocity is increased from 30 meters per second to what? 60 meters per second. Because it's happening like that, so they have given the thing like this. To nozzle. So from the turbine is entering a nozzle. What will happen to C4? Now C3 is 60 meters per second. What will happen to C4? What will be the value of C4? Whether it will be less than C3 or more than C3?
Less than.
Less than. What is of nozzle?
Increase the
Increase the
velocity.
So C4 should be?
Convergent divergent also. In divergent position it may.
No. You may get confused because of using the convergent divergent nozzle. The purpose of a convergent nozzle is that it can increase up to sonic velocity only. Whereas in case of convergent divergent nozzle, the velocity can exceed more than sonic. It can become supersonic. But the purpose of the nozzle is always to increase the velocity and not to decrease. So what he thought in his mind is that after the convergent region, the velocity may increase. In the diffuser region, the velocity head may reduce and it may increase the pressure. Like that he thought. It's not a combination of convergent nozzle and diffuser. It's called a steady nozzle only.
Yes.
So the purpose of a steady nozzle is to have Mach number greater than 1. What is Mach number? Mach number is nothing but C by A. C is nothing but velocity of the fluid by velocity of sound in air. Generally, this A value is 330. So, if for example, if I am going to have the velocity to be 450 or 460 or I will have 660. Now, what will be my Mach number? 2. This can't be achieved with the help of convergent nozzle. With the help of convergent nozzle, I can go only up to what? 330. I can't go beyond what? 330 meters per second because the convergent nozzle will go up to sonic only. But if you want to increase the velocity beyond the sonic velocity, then I have to use a convergent divergent nozzle. Generally, in a turbine, we need a convergent divergent nozzle. But the drawback with the convergent divergent nozzle is that some shock waves will be formed in the divergent portion. That let us discuss separately, not here. We can't spare more time. So his doubt is clear. So even though it's a convergent divergent nozzle, definitely the velocity at the exit should be more than what? The velocity at the entry. So definitely C4 will be greater than what? C3. Even it can exit sonic velocity. Let us try and see. Let us see what is the temperature, what is happening to the temperature also. Now the thing is velocity and the temperature has fallen to, the T4 has fallen to 500 degrees Celsius. So 500 plus 273 is nothing but 773 Kelvin. Is 773 Kelvin. So what happened? It has fallen from 923 Kelvin to 773 Kelvin. So what is the question they may ask? with respect to the nozzle?
Is the final velocity.
What is the final velocity? Or how much velocity has increased in the nozzle? So the question will be C4 is what? Okay. Then what is the question in the turbine? How much amount of power is developed? Whenever we using dot, it is the rate, work rate. Work rate is nothing but power. What is the question they can ask in the heater? How much amount of heat is added? How much amount of heat is added? So what is the working fluid? Is air. What is the working fluid? It is air. And they are telling the mass flow is not 1 kilogram, but the mass flow is 2 kilogram. Generally, the steady flow indication is meant for what? 1 kg. Yeah, per unit kg. Yeah, per kg. But here, the mass flow rate of air is not 1, but instead of 1, it is 2 kg. In some problem, they may give 5 also. Some problem, they may give 0.2 kilogram also. It need not be 1 always. It can be either less than that or more than that. So, I will repeat the problem once again. Air is entering into a system of open flow systems consisting of heat exchanger, turbine and a steady nozzle. Here a temperature of 15 degrees Celsius or 280 Kelvin with the velocity of 30 meters second enters into heat exchanger where the outlet temperature is increased to 1073 Kelvin but the velocity remains the same. So the temperature has increased from 288 to 1073 Kelvin. What is the how much amount of heat is being added? That is the first part. In the second part, the air is coming at a velocity of 30 meters second where the temperature is 1073 and is going to get expanded in the turbine. And in leaving the turbine, it has a property like velocity has increased from 30 meters second to 60 meters second and temperature has dropped from 1073 to 903 Kelvin with a positive power output. So what may be the question? How much amount of power is generated in the turbine? The third part is on leaving this turbine is coming the velocity of 60 meters second and temperature of 903 Kelvin is going to pass by a seat nozzle where it will finally going to hit the temperature of 773. There is a temperature drop. So what may be the question? How much of velocity has been increased or what is the exit velocity? So we know what is the question now. And also we know the mass rate of air is 2 kg, it's not 1 kg. It's not 1 kg. Now let us try to solve it very easy. The formula is saying H1 plus half C1 squared plus GZ1 plus Q is equal to H2 plus half C2 squared plus GZ2 plus W. In a heat exchanger, there is no moving components, which means what? W equal to 0. In this problem, they have not mentioned anything about the height. So we can assume Z1 equal to Z2 and we can cancel this Z1 and Z2. What is Q? Q is nothing but Q1 to 2. That means how much amount of heat is added to the air by this heater is nothing but what? Q1 to 2 is equal to what is the formula then? H2 minus H1 plus half into C2 squared minus C1 squared. So let me erase this one. Temperature T2 is 1073. So I write it here. So T2 is equal to 1073 Kelvin. Okay. What about C2 and C1? They are same 30. So this also will go away because in the problem they are given C1 equal to C2. So this term also goes away. So what is Q1 to 2?
H2 minus H1.
What is H2 minus H1? What is the formula? Cp into T2 minus T1. What is Cp for air? You should know. In the problem they won't give. So you should know for C. The Cp of air is 1.005 kilojoule per kilogram Kelvin. So you substitute here as 1.005 into 10 power 3. Don't forget to multiply by 10 power 3 because we want to convert the kilojoules into joules. Okay. Kilogram there is no need to change. There is no need to change the Kelvin. But there is need for converting the kilojoules into joule. So I multiply by 10 power 3. What about T2? 1073. What is T1?
288.
288. So what is the answer? So 1073 minus 288 into 1.005.
7,88,000.
No, you can tell into 10 power 3.
Okay.
1073 minus 288 into 1.005.
788.9.
Yeah, that only it comes. 788
0.925.
0.925 into 10 power 3
Yes.
joules. If I once again go to divide by 1000, it becomes what? Kilojoules. So instead of this 10 power 3, I can put as what? Kilojoules. So 788.925 kilojoules of heat is required to raise the temperature from 288 Kelvin to 1073 Kelvin. For how much amount of mass?
For 1.
Yeah, because we have used only small letters for 1 kilogram. But in the problem they have asked for what? 2 kilogram of mass, because the mass flow rate is not 1 kg, it is 2 kg. So the answer is what? We have to multiply this answer by what? 2, because they are asking for 2 kg. So 2 into 78 point, what is the answer?
1577.85.
1577.85 kilojoules per second. What is the unit? It is not only kilojoules. Now the mass is not mass, it's mass flow rate, kg per second. So it's kilojoule per second. What is kilojoule per second? Is kilowatts. Kilowatts. So whether it's positive or negative? Whether this value is positive or negative?
Positive.
What is positive means?
It is gained heat.
Heat is added to the system. You get a tell like this. It is gained heat. Yes, gained heat. Or heat is added to the system. So it's endothermic reaction. So what does it mean? 1577 kilojoules or kilojoule per second amount of heat is required to raise the temperature of 2 kilogram of air from 280 Kelvin to 1000 Kelvin. Are you okay? I hope it will be very clear. I hope it will be very clear. Now shall we move to the next topic? That is turbine. Let us take the case of turbine. Once again, the states is from 2 to 3. The inlet is what? 2. The exit is what? 3. So now I can write like H2 plus half C2 squared plus GZ2 plus Q 2 to 3 is equal to H3 plus half C3 squared plus GZ3 plus W 2 to 3. Isn't it? Instead of 1 and 2, I am writing it 2 and 3. The inlet is 2, the exit is what? 3. Now, what they are given is nothing but, what about the heat transfer? There is no heat loss from the turbine to surrounding. We assume it is adiabatic. If there is no data given in the problem, we can assume the heat loss of the turbine to surrounding is nil, or it's adiabatic, or it's perfectly insulated. So Q to 3 is 0. What about Z1 Z2 or Z2 and Z3? They have not given any data. We can assume Z2 equal to Z3. So what is the final expression? We have H2 plus half C2 squared equal to H3 plus half C3 squared plus W 2 to 3. From this we want what only? W 2 to 3, which is nothing but what? H2 minus H3 plus half of C2 squared minus C3 squared. So what is H2 minus H3? Cp into what? T2 minus T3 plus half of C3 squared minus, C2 squared minus C3 squared. So what is Cp? It is 1.005 into 10 power 3. Don't forget to multiply by 10 power 3 because we are converting kilojoules into joules. Into T2. What is T2? T2 is 1073. What is T3? T3 is 903 Kelvin. Okay, let us write these values in the bottom. So T4 is 773 Kelvin and C4 is what? Okay, plus half into, what is C2? C2 is 30 squared. What is C3? 60 squared. Because all these values we know, just substitute the values and get the answer. So now you will get W2 to 3. You first tell me this value alone. First you tell me this value.
150750.
150750.
0750.
You multiply with 10 by 3 also.
Yes, sir.
Otherwise it is 150750, isn't it?
Yes.
Okay. Otherwise you got a value of 150 into 10 power 3.
Yes.
Yeah, nothing wrong in it. Plus, what about this value?
Minus 1350.
Okay, fine, good. Minus
1350.
1350, isn't it?
Yes.
You now subtract this value.
149400.
14
400.
400. What the unit is? Joules.
Joules.
It is nothing but what? Joules. If I am going to divide by 1000,
Kilojoules. 149 kilojoules.
it will be 149.4 kilojoules. So the power developed by the turbine is equal to 149.4 kilojoules for what is the mass?
For 1
For 1 kg of air, the power produced will be 149.4 kilojoules. If I am going to send 2 kilogram of air, then what will be the power? It will be twice of this. It will be twice of this. So it's not W1 to 2, sorry, it's W2 to 3. So this is the power produced by the turbine when 1 kilogram of air is sent. But we are going to find what the amount of power generated when 2 kg per second of air is passed. So it is 149.4. The unit will be what?
Kilojoules per second.
Kilojoules per second. Very good.
Kilowatts.
So it will be kilowatts. So what is the answer?
298.8.
298.8 kilowatts. I hope you can easily understand. It's not difficult. It's very simple. Now I have taken a problem which will take care of all the open flow systems at the maximum. So the power generated in the turbine, there is positive or negative.
Positive.
Whether your answer should be positive or negative.
Work is done by, work is gained by the system.
Yeah. Work is not
Not
gained.
gained.
Work is developed by the system. Work is developed by
Developed.
the system or work producing device.
Yes.
So it's positive, it's right. If you are going to end up with negative, then you made some mistake. So W should be what? Positive only.
Positive.
So it's also right. So it's also right. So now let us try to come to the last area. There is nothing but a steady nozzle. So CD nozzle. What is state? It is from 3 to 4. So it's H3 plus half C3 squared plus G Z3 plus Q 3 to 4 is equal to H4. The same formula only. I am not changing the formula. Plus half C4 squared plus G Z4 plus W 3 to 4. Whether the nozzle have any moving components?
W.
No. So W is 0. Also, as I assume the nozzle is perfectly insulated. So what happened to Q?
Q also
0. What will happen to Z3 and Z4? We assume they are about the same height. So Z3 equal to Z4. So finally what will end up? I hope I can erase now these things. So what is the final thing we end up now? H3 plus half C3 squared is equal to H4 plus half C4 squared. What is the unknown here? We have to find C4 because H3 is known or H4 is known or H4 minus H3 is nothing but Cp into T4 minus T3. So T4 is given, T3 is given, C3 is also given. So only unknown is what? C4. So one expression, one unknown, we can easily find it out. Otherwise I will write here half C4 squared is equal to H3 minus H4 plus half C3 squared, isn't it? Otherwise C4 squared is equal to 2 times of H3 minus H4 plus half C3 squared. So it is 2 into Cp into T3 minus T4. Cp is 1.005 into 10 power 3. What is T3? T3 is 923. What is T4? 773. Isn't it?
Yes.
Plus half into what is C3? C3 is 60 meters per second. So it is 60 squared. So what is the answer? It is let us say it is now C4 squared, not C4, but C4 squared. So what is the answer?
That one is 150750.
This one is
150750.
150.
750.
Okay. What about this one? Yeah, this one.
1800.
1800. Okay. Whether it is positive or negative? Positive only. Yeah. Fine. Now we multiply this one.
305100.
I multiply 2. Yeah. 3.
305100.
3051.
00.
00. It is C4 squared. Can you take the square root of this one?
552.35.
552.35 meters per second, isn't it? I want the unit very important. Now this is the velocity for 1 kilogram of fluid. Now what is the velocity for 2 kilogram of fluid? Tell me the answer.
Into 2.
Divided by.
The velocity is an intensive property which doesn't vary with the mass. Whether you are going to have 1 kilogram also, the velocity will be same. Whether you are going to have 0.1 kilogram also, the velocity will be same. Whether you are going to have 10 kilogram of gas also, the velocity will be same. So please don't multiply by the mass. because the velocity is a intensive property. Otherwise, I can tell here also in the same expression. What is kinetic energy? It is half mv squared. What is enthalpy? M into H3. What is enthalpy? M into H4. What is this one? Kinetic energy half mv squared. So all the terms contains what? Mass. So we can strike off the mass also, which means the velocity is independent of the mass being taken. So in the examination, please don't multiply by 2 for the velocity. Otherwise, I give the result because I multiplied the mass everywhere, but I found the velocity is independent of the mass. So I hope this session may be useful for you to understand the first law of thermodynamics applicable to a open system for various devices like heat exchangers, turbines, compressor, fan, pumps, throttle valve, etc. etc. And we have taken a numerical problem to understand more clearly. Thank you. I also wish to thank my students Arun Sako and Mr. John Samuel for actually participating in this session as well as they are making this video. Thanks them also. Thank you.